A former NASA scientist claims that he and his team have built a device that defies gravity. No propellant, no exhaust, just electricity and measurable thrust. Every rocket ever launched follows this one principle. Chemical fuel is burned, mass is expelled, and momentum carries the spacecraft in the opposite direction. If the claims are real, it challenges some of the most fundamental assumptions in physics. So, what exactly is being claimed, and how seriously should we take it? Charles Buhler is a physicist and engineer who previously worked at NASA's Kennedy Space Center, where he helped establish the Electrostatics and Surface Physics Laboratory. His background includes work on spacecraft charging, electrostatic discharge protection, and dust mitigation systems for space missions. In a recent interview, he stated that his team has developed a propulsion system that can generate thrust without propellant, without reaction mass, and without relying on known effects like ion wind. According to Buhler, the system can produce enough force to overcome Earth's gravity, at least at small scales, using only electric fields. If true, this would represent a direct challenge to one of the most established principles in physics: conservation of momentum. Over the years, many propulsion concepts have promised thrust without reaction mass. Almost all have collapsed under closer examination, usually because of overlooked experimental errors or misunderstood physical effects. That history is important because it shapes how scientists respond now. Buhler himself acknowledges this skepticism. He does not frame his work as proven new physics. Instead, he describes it as an observed effect that is not yet fully explained and that must be independently verified. Any discussion of propellant-less propulsion inevitably returns to one earlier example, the M drive. The M drive was a proposed propulsion device that claimed to generate thrust without using fuel. It was introduced in the early 2000s and attracted attention because it appeared to break a basic rule of physics, that a spacecraft must expel mass to move forward. The idea was that microwaves bouncing inside a cone-shaped metal cavity could produce a small net force, even though nothing was pushed out. Early experiments reported tiny thrust signals, including tests linked to a NASA research group. But later, more careful studies showed those signals could be explained by experimental errors such as thermal expansion and electrical interference. When those factors were controlled, the thrust disappeared. By around 2021, the M drive was widely considered disproven and is now used as a cautionary example of how easy it is to mismeasure extremely small forces. Buhler's work enters this landscape fully aware of that history. Buhler does not claim to be refining the M drive. In fact, he explicitly distances his work from microwave-based propulsion. Instead, his team focuses on electrostatics, the physics of electric charges and electric fields. Electrostatics is well understood. It governs how charges attract, repel, and store energy in materials. It is used every day in capacitors, sensors, and spacecraft systems. The unusual claim is not about electricity itself, but about how electric fields interact with matter under specific asymmetric conditions. According to Buhler, the key concept is asymmetry. In simple terms, his team argues that if an electric field is arranged in a way that is not spatially balanced, meaning the pressure exerted by the field is different in one direction than another, then the system may experience a net force. He describes this as an effect arising from electrostatic pressure, not from expelled particles or airflow. In most systems, forces cancel out. Push in one direction, and there's an equal pushback. But Buhler claims that certain configurations of materials and electric fields prevent this cancellation, allowing a small net force to remain. This is what he refers to as a new force, though he also emphasizes that it may be an extension of known physics rather than a violation of it. One of the biggest challenges in experiments like this is ruling out ion wind. Ion wind occurs when high electric fields ionize air molecules, creating a tiny but real airflow that can push objects. Many historical anti-gravity experiments were later explained by this effect. To address this, Buhler's team reports that they encased the devices to limit interaction with air, operated them at lower voltages, moved testing into high vacuum environments, and ran experiments in hard vacuum, where ion wind cannot exist. These steps are necessary, but not sufficient. Eliminating ion wind removes one common explanation, but many others remain. One detail that lends credibility to the narrative, though, not the conclusion, is the timeline. According to Buhler, the team spent years testing devices that produced either no thrust or forces far too small to matter. Many early designs produced results similar to historical asymmetric capacitor experiments, with thrust levels close to experimental noise. The reported change came around 2020 to 2021, when the team altered the internal structure of the devices. Instead of traditional capacitor geometries, they moved toward thin film, two-dimensional structures that emphasized interactions between electric fields and dielectric materials. This shift coincided with higher measured forces. A key technical distinction in Buhler's explanation involves two types of electric charge. Free charge is what moves through conductors, like electrons flowing through a wire. Bound charge exists inside dielectric materials, where charges are not free to move, but can shift slightly under an electric field. Buhler claims that configurations dominated by bound charge effects produce stronger thrust than those relying mainly on free charge. The idea is unusual, but it isn't meaningless. Materials can feel internal forces when electric fields are applied. The real question is whether those forces can add up to a measurable push on the outside. If you genuinely enjoy exploring the universe and its mysteries, consider subscribing. It helps us keep going. One of the most attention-grabbing statements is that some experimental configurations reportedly produced thrust exceeding 1 g relative to the mass of the device. This does not mean the device lifted itself off the table like a levitating object. It means that, when normalized by mass, the force-to-mass ratio was comparable to Earth's gravitational acceleration. In laboratory physics, such normalization is common, but it can be misleading to non-experts. What matters is not the ratio, but the absolute force, the measurement method, and whether all alternative explanations have been eliminated. So far, these results have not been independently published in peer-reviewed journals. At present, the evidence consists of internal laboratory measurements, conference presentations, interviews and technical discussions, and claims of limited external replication by small research groups. What it does not yet include are peer-reviewed publications, independent replication by major laboratories, space-based testing, or a widely accepted theoretical model. This places the work in a familiar category: intriguing, unresolved, and unconfirmed. It is tempting to assume that because someone worked at NASA, their claims carry institutional weight. Buhler has been explicit that this work is not affiliated with NASA and that his views do not represent the agency or the US government. Science does not operate on authority, it operates on reproducibility. A claim is either supported by independent data or it isn't. Despite skepticism, many physicists are paying attention for a simple reason. If an experimental result continues to appear under increasingly controlled conditions, it becomes harder to ignore, even if it contradicts expectations. Extraordinary claims require extraordinary evidence, but they also require patience. The history of physics includes examples where strange results were initially dismissed, only to later become accepted once better data emerged. It also includes many more examples where strange results vanished under scrutiny. For this claim to move from curiosity to credibility, several steps are needed. Independent laboratories must reproduce the effect using their own equipment. The results must be published with full experimental details. The measurements must hold up under blind testing and careful error analysis, and competing explanations must be systematically ruled out. Until that happens, the claim remains provisional. Even if the effect turns out to be illusory, The process matters. Investigating edge cases tests the limits of experimental methods. It forces better controls, sharper theory, and clearer definitions. And if the effect is real, even at very small scales, it would have implications far beyond propulsion, touching on materials, science, electrostatics, and fundamental physics. What happens next? Buhler says the near-term goals are continued lab testing, refining the device's geometry, gaining additional independent verification, and securing funding for broader studies. Space-based tests, however, are still a long way off. Until then, the story remains open not as a breakthrough, but as a question still waiting for an answer. If an effect like this does turn out to be real, what do you think should come first? Deeper laboratory testing, independent replication, or an attempt to build a space-based experiment? Let us know what you think in the comments.